Hello everyone, I hope you're doing well. Today I'm here to be presenting you basically a recap of what we did in section 2. So just as a heads up, all of the questions that we will be doing, the timestamps will be in the description below. So this week we're doing algorithm analysis, and so this is the worksheet. The link to it is right here, or you can of course go to our website, click on a blank worksheet. So we're gonna go ahead and set the logistics, and we're gonna start with essentially basic big O. So as a recap, based on 143, we have a bunch of complexity classes, constant, logarithmic, and so on. As you can see in the table here, as you go down, it has basically worse runtime. For example, here a constant runtime will be better than logarithm runtime, and then so on right here. All right, so some basic rules that you may have learned from 143 is that exponentials dominate polynomials, order polynomials dominate lower order. For example, n to the power of 4 will always dominate n to the power of 3 and 2 and so on. Polynomial always dominate log, and log dominates constants. And we'll follow with sort of the proof later on in the video. All right, so when we're analyzing these things, it's important to note that we don't care about constants, because in all of these, we're going to be assuming that n is approaching infinity. All right, so for example, 750 million is minuscule compared to whatever n is going to be. All right, so first of all, we're going to be doing problem 1a and problem 1b, which is comparing growth rates. So what we're trying to do here is we're going to be simplifying this a type go and then we're going to be sorting them from the fastest growing to the slow growing in terms of their growth rate. All right, so let's look at this first one: log base 4 of n plus log base 2 of n. Now we want to essentially erase the bit that is not being that is being dominated, right? So in this case, we want to know, okay, which is dominating which, log base 4 or log base 2? So just mathematics, we can use the change base formula to convert logarithm's base number to anything we want. So specifically, the base formula works like this: log base b of x equal to log base d, and d can be any number of x divided by log base of the number of b. So in other words, what we can change log base 4 of n into log base 2 of n divided by log base 2 of 4, and log base 2 of 4 is just 2. So essentially, this bit right here that we're putting in the denominator is just a constant. And remember, when we're doing these kinds of analysis, we're ignoring all constants. Essentially, what we can do is ignore completely. Log base 4 of n is approximately log base n. And it turns out that we can convert a log of any base into a log of any base. And so what we generally do is anything, log base anything is just going to be in complexity of log. All right, so that's why we see omitting the base altogether, because we can just convert them into change base formula. So ultimately, this is by doing change base mathematics, we get 3.5 times log base of n. And when we convert to the big O bound, as in we the constants, we get O of log of n. All right, and the next ones are a little more straightforward. N over 2 plus 4, we erase the constant 4, and since it's essentially half times n, we read it as well. So it's going to be n, which is in big O of n. So 2 to the n over 3, the constant 3, that's going to be 2 to the n. 750 million, and over here, since 750 million has absolutely no relation to n, as in an increase of n doesn't change the value of 750 million, this should be a constant. Because remember, when we're thinking of n approaching infinity, these numbers are considered super small. Like 700 million is a minuscule compared to what we're going to be dealing with. So this complexity is just going to be O of 1. Right. Lastly is n plus 4n squared. We see that squared is a higher order polynomial, so it dominates 8n. to be erased completely. And to drop in constants, it's just going to be n squared in terms of the complexity. All right. So now we're going to be ordering from the fast growing to the slowest. Now, I want to be specific here. When I say fastest growing, it means that it increases most as n increases. So in terms of the runtime, it's actually slowest to fastest in terms of the runtime if we would run code with these kinds of complexities. Right. So the fastest growing would be an exponential. So we have here to the n. Following an exponential would be a polynomial degree. In this case, we have n squared. And O of n to the polynomial of order 1 followed by log of n followed by constant. Yeah, and just a quick note that complexity class of exponential takes really, really long to run, because if you think about it, if n is, let's say, just 10, that output would be around more than 1,000. So yeah, try to refrain from writing code that is an exponential complexity. All right, now we're going to be doing 1b. So let's start with this first one. 2 to the power of n over 2. Is it its own complexity, right? Or is it part of 2 to n? It turns out that even though it seems that way, if we do a little math again, it doesn't actually work. So let's give an example here. And I want to note that 2 to the power of n over 2 is 2 to the power of half n. So now let's take a different sort of constant exponent. Instead of half, we're going to 2. And note that 2 to the power of 2n is the same as 2 to the power of n times 2 to the power of n. Now we can't just drop one of them, because let's suppose that let's consider a different example where this is n times n. We can't just say that n times n squared, right? We can't just say that n squared is the same with n. So that's why we combine these two together, so this becomes different. So the constant in the exponent cannot be removed. So it turns out that 2 to the power over 2 becomes its own complete class. All right, the next one, 3 to the n, no constants to drop. So that's 3 to the n, a complexity class inside, followed by 2 to the n, which is the same thing, its own complexity class to the n. So now we're going to be sorting which of is fastest growing to the slowest growing. So the answer is going to be 3 to the n, followed by 2 to the n, followed by 2 to the 2. A general rule of thumb is that if you look at the base first, a higher base will always lead to a faster growing function. If we have two functions of the same base, for example, 2 to the n and 2 to the 2, we look at which constants or exponents are small. All right. So up next is a lot of math and talking about the 3 bounds we did this lecture. The big O bound, this one here, and this one's big theta, and it's called big theta. All right. So essentially, what big O means is that it is an upper bound to how the a function goes, and big omega is lower bound, and big theta is down. It's easier to visualize this way. For example, here O and log n, any function that is bound by n is part of O and log n. Inversely, any function that is lower bounded by n log n, or rather of n log n, is part of big omega again. So then how do we get to big theta of summation? Well, it turns out that it has to be both big O of the function and big omega of the function. In essence, when you look at the graph, f right here will also be squeezed between two D's. We'll get to an example that becomes clearer in a minute. All right, so right now we're doing 2e, b, and e, which is just a true function. So we have 2e. If a function is in big omega of n, then it could also be in n squared. Let's first discuss what big omega of n means for our function. Well, it means our function has to go at least as fast as n. For example, a function n would be just as fast as n, but n squared would be faster than n. So both be valid function be within omega of n. What does O big O of n squared mean for a function? Well, inverse. It means function will grow most as fast as n squared. For example, a proposed function could be n squared, where n squared is as fast as n squared. But let's say a function like n3, that would be an O of n squared that is faster than n squared. Right. So in order to visualize this, we need to sort of propose a function that is in omega of n and also in O of squared, because that would prove the statement is valid. Open it. This proof. So our proposition is black and right. I equal n to the power of 1. And notice here the that is in big omega of n. So I pick n applied constant, which in this case I choose 0 and 1. And you'll know after 0, my function is all bounded this green function, which is multiple of n, right? So that means that the y equal n to the power of 5 is in omega of n. You just have to prove the way around. So we want to prove that our function can be over by n squared. And so I just chose y equal n squared, and you'll see that this function to infinity is always going to be bound to this black function. It means that yes, indeed, our black function is bounded by n squared, which means that our function y equal n to the power of 1.5 is big O of n squared. So we find function is big omega of n and big O of n squared, means that is true. And next, this statement, if the function is in beta of n, then it could also O of n squared. First of all, what does it mean our function be big theta of n? It means that it's bound by, right? And it's sort of this squeeze that I'm showing in just a minute. And same thing before, it means that our function is at most as fast as over as squared rather. So it's the so first of all, my host function is right here. So if this function is in theta of n, to do that, we need to have two of n will squeeze that function. What that is that it'll have something as a lower bound and something as an upper bound. In this case, 1.1n as a purple here, and I have 9n as the blue line right here. And you can see those which are a multiple of n is actually squeezing our close to 1n. Which means that n is in O. The other is that our function y is in O and so which is lower and lo and behold, if I just after this point y, this black n is bounded by n squared and is in O n squared. It's turned out to be true as well. Next would be if a function is in beta, it is always of. So what does big of n mean for a function go at least as fast as n, and that will go as slow or slow as n, right? So if we find a function that is in big of n but not in O n, it means that this one is false. I have my proposed function is equal where I can see if I put y equal n, with n, blue function is lower bounded. I mean, this function will always be lower bounded by blue. What it means is, what that means is that that x squared area of n. Now, the other thing that we want to sort of check, like, will this function be in open as well? I have to find some c such that the blue function will be an on for the red function towards infinity. And it turns out it's actually impossible to do that. So if I set an at this point, the red can be upper bound to the lower function. Otherwise, and no matter like how big it becomes, it's simply not possible. And this that function squared is not in big O, which means that we found a function and that is in big omega of n, but not in big O of n. This so that's gonna be pretty much most of the math we'll be doing. We'll be doing one of the things now, like code. So let's go over 4a of our worksheet. So we have this function. We want to be doing a cool model of that. First line n equals 0 is doing just constant work, and this loop operates n times. Actually, operates n squared over 3 times. This one is doing constant work. So notice here that this loop inner loop does n squared over 3 work in total, right? Like square root 3 times work. Then it is nested within something that operates n times. So in total, this will operate n times n over 3 times. And so our recurrence will be n to the power of 3 divided by 3. And there's probably some constant where we're dropping. And so from this model, we can get our bow bound, which is constant number 3. And so the worst case time of a function is going to be n squared. I mean, n to the power. All right, now for b, so just we have constant work right here. But so this if we add it, it seems that all n times, right? We start I at n, and we reduce I until I reach 0. But it turns out that this breaks the same as potential. It will break whenever I is divisible by 2. And I argue that this will always happen with 3 equations because we're I only by 1. After either the first, the second, or the third iteration, this loop, this requirement is satisfied this. So at times the ways you only do 3 times 4, with 4 here equal to 12. We're only doing 12 in total within the. So in total, model is essentially 13 work, and surely enough, that's going to be a constant big O. Right, so I want to sort of make it clear that what we're doing so far is asymptotic analysis. We're not doing case analysis. Because everything so far only depends on one variable, which is n. When we're doing case analysis, it has to depend on something else. So let's say we're saying n is the size of the array. In order to do case analysis, we have to depend on something else. Say it depends on the input of the function, or it depends on the state of the array. All right, so I'm sure that we have to make analysis. This is just analysis. All right, but we're going to be doing some cases now. 5a. So we have this function with an array list. So array list is sort of this data. Right? So there's array, and what it's doing is actually I want to insert some x. And so let's walk through the code. So it says equal size. Remember, basically within the array so far. So right now, element is 4, and I'm going to be I until I reach the index I want. At index, I will be copying my neighbor to the data I equal data I minus 1. So let's walk through right here. I try one comma. I start as size, and then I a copy. So 20 copy over 4. And I when I and I do the same thing, copy then I and I over. At this point, I is equal to index, right? And this requirement is and data index equal to value. So this change. So let's think of a case scenario that is, by the way, not taking size of an array. So it has to depend on something else. That will give a good runtime. So in actual, the best case is going to be constant. Suppose we insert to the end of the then we don't have any of the elements. So suppose I call insert x20. So I start at 5 right here, and this element never even fulfilled from the beginning. So this for never happened, and then so it becomes time to do this. This is right here. So how about the worst case? Case is going to be a linear run. We in the beginning of the list, which means that I have to move all the elements, or in others, it will be the entire size of my list. So if I do insert 0, so I start from here, and I have to start from 5 there, and I move over 9, move 15, move over 50, move over 8, and then insert here. Right? And so it cost me essentially 10 linear. So notice here that best case slash worst case can't just be like, oh, if the array is empty. And it's easy to think that because, like, of course, if the array is empty, it will be constant runtime. But remember, we're thinking of things that are unrelated to n. Very unrelated. Since n at the moment is referring to the set of the list, we can say, oh, if the set of list is empty. So it has to depend on index, value, or the state of our current list, but not just purely its size. All right. So to finish this list problem, let's just walk through it real quick. Actually, if I try to get R, remember this is value prepared, key out, value 8, key R, value 11, key U, and value 13. When I do R, I start at front and say, okay, this is not it, so the key is equal. If this goes here equal to this key, and how it's not equal to R, so this is up and I can compare it by 1. Okay, it turns out that when we go to the next one, key R is equal to key by the U. And so I call it turn instead, and I which is 11. Now again, let's up the best case which is a key exists in the front of those means that I have to do this, but I have to go to the next, right? So if I have stop iterating in the front node, which means it would just be constant runtime. Is linear if it doesn't exist in the list at all. The means is that I can do all of the nodes for figuring out if it even exists. If I said which doesn't exist within any of the nodes, I will go through how and R U, and I'll go and I right, and so I would iterate the entire size of our list. So that's actually it for case, and now we're going to go to the formal definition. So we're going to be discussing this. So far, we've sort of like, oh, exponentials always dominate polynomials, higher polynomials always dominate lower ones, and so on. what exactly does dominating mean, right? So this is going to be the formal definition of big O. F is big O of GON if there exists some positive constant C and N naught, such that for all s above N naught, as in from towards infinity, Fn is always less than or equal to our constant C times function G, which is in this big O. It's all right. So now let's try to sort of prove this using problem 6a. All right. So what 6a is trying to do is we're trying to prove that 3n plus 4 is in big O of 5n squared. But instead, what we're going to be doing is we're going to be sort of splitting this up into sub-problems. First of all, we're going to be proving 3n is in 5n squared, is in big O of 5n squared rather, and 4 is in big O of 5n squared as well. All right, so the first sub-problem, we want to show that 3n is in big O of 5n squared. So we have to find some magic numbers C and N naught such that the requirement for big O is fulfilled, right? So we'll start with this inequality, and we have to think of C and N naught such that starting from N naught and so on, 3n is always less than C times 5n squared. So first of all, let's think of the C. So the idea here is that I want to try to make it so that the left side and the right side look similar. I want to pick some C, which doesn't have to be an integer, it can be any constant, such that the left side and the right side look similar. So in this case here, what value of C would sort of make my coefficient similar, right? So in this case, if I pick C equals 3 over 5, I'll get 3 over 5 times 5n squared, which becomes 3n is less than 3n squared. Now over here, it sort of seems more obvious why this is the case, right? All right, so next up we have to pick some n naught such that after n naught, all values of n up to infinity, this inequality is always going to be satisfied. So in this case, this inequality is always going to be satisfied when n is above 1, right? And then so what I'll do is I'll pick n naught equal to 1, right? So the two magic numbers that I've thought about, C is going to be 3 over 5, and n naught equal to 1. And just like that, we've proven that 3n is in big omega of 5n squared. All right, so we've done that proof, and now we're going to be going to the second subproblem. So same thing, start with the inequality. We think of a C that will make the left side and the right side look similar. In this case, let's say 4 over 5. And then so we get this inequality. And then so for what value of n naught is it that this inequality is always true starting from n naught up to infinity? It's going to be, sure, let's say n equal 1. I mean, n is more than 1, right? So starting from n naught equal 1, this inequality is always true. And just like that, we've proven that 4 is in big O of 5n squared. Now, I want to note that for this example, and so as the previous example, this one, these are not the only C and N naught available. You can give any C and N naught as long as this inequality is satisfied. And it's the same proof. It's proving that, f of n is a big O of g of n, or in this case, 3n is in big O of 5n squared. So these are the numbers that we happen to pick for this example. Even for this problem, you can pick infinitely many C's of n and n naughts. So we've proven these two things. 3n is in big O of 5n squared, and 4 is in big O of 5n squared as well. So here's what we can do now. We're going to try to combine the sub-results for our complete proof that 3n plus 4 is in big O of 5n squared. So how we're going to be doing it is we're going to be adding the inequalities. So on the left side now we get 3n plus 4 is less than or equal to 3 over 5 times 5n squared plus 4 over 5 times 5n squared when n is more than or equal to 1. Right? So we're just adding up these two subproblems. Right? And we can see that 3 over 5 and 4 over 5, they sort of become like constants that group around. They are grouped around right there. And then so if we add this up, it becomes 7 over 5. And notice here that we just found a C and n naught immediately from our subproblems C equals 7 over 5, right, by adding these up. And N naught equal 1, because it follows from the previous inequality. And so now we've just proven that 3n plus 4 is equal to big O of 5n squared. So that's actually everything I have for you today. Feel free to drop a question on Piazza or drop by office hours if you have any further questions in section. And I hope to see you next week in section.